The kinetic molecular theory of gases, or the KMT, has to do with the actual definition. If we just take a look at the definition, it kind of describes how this thing works. Kinetic, if all you out there know that that means motion. So the motion or the movement of something. What is that something? It's the molecules. And of course, theory means that we've tested this over and over again to come up with some type of really conclusive evidence or statement. So the kinetic molecular theory has to do with particles, molecules, atoms, ions. They're constantly moving in the form of gases. So the 4 points of kinetic molecular theory, you can read them here just as I can. Gas particles are small with tremendous spaces between them, and the velocity of the particles is the volume of those particles is equal to zero. So if I have a tremendously large space, I know that's not a huge space, but if I have a large space, then I have just a couple molecules in there, and they're very, very small compared to the amount of space that's between them. Okay, if I were able to collect all these particles in one simple area, the volume of those particles would be zero. That's what we assume. All right, we also assume that the particles are in constant motion. So they're always moving, especially gases. The next one, there's no forces of attraction between gas particles. Now, we haven't talked about this yet, but this has something to do with, it's called London dispersion forces. You can disregard the statement, but what happens is real gases slightly attract each other in the fact that as they fly by each other, there's a little bit of force of attraction. We're going to say that if you have an ideal gas, a gas that follows all parts of the kinetic molecular theory, you're going to say that there are no forces of attraction. Okay, so they don't attract each other at all. All right. This has implications. In other words, this is constant diffusion. Gases will constantly diffuse themselves, which is the random mixing of these gases, and so on. Last particle, or the last statement, is that as the average kinetic energy increases, the average Kelvin temperature increases. This basically says that hot particles are moving faster. So hot particles such as temperatures in 120, 130, 150, 300 Kelvin, so on, they're moving much faster than particles that are moving at 50 Kelvin or 100 Kelvin. Okay, so that is indicative of that. Also, you'll also notice that the kinetic energy equation is 1/2 mv squared. What this says is that the particles that are more heavy have a greater kinetic energy. Okay, this is assuming that particles that are heavier and particles that are lighter are traveling at the exact same velocity. Okay, so that we can manipulate this equation in a couple of different ways. For now, we'll just keep it simple. All right, next. All right, kinetic molecular theory applied. All right, what if I have pressure and temperature? If I consider pressure and temperature and keep volume constant in this first example right here. Oops, let me get back to this. So if I have this first example, pressure and temperature are going to change, volume is going to be constant. And what we have here is this is typically going to be something with a rigid container like an aerosol can. Aerosol, I don't know if I spelled that right. Anyway, an aerosol can is a rigid container. So here's the nozzle, here's the can, and so on. That's a pretty good can. Anyway, what happens is if I take this can with a constant volume and throw it into a fire, the volume stays constant, but what happens to the particles? The particles start to move faster. They start to gain their kinetic energy. Anytime the particles are moving faster, they're causing more collisions against the sides of the container. As they create more sides of the container, pressure increases. As pressure increases, because temperature increases, eventually this thing will explode. Okay, and then the volume isn't constant anymore. So, in a constant volume container, as temperature increases, pressure builds or pressure increases. Okay? Next, volume and temperature. We will talk about this, but we will keep pressure constant in this case. So this might be a balloon. That's a really bad balloon. Or it could be a piston. So this is a movable piston. Here's my volume inside here, and the piston moves up and down. Okay, so pressure stays constant here. So what happens with temperature? If, let's say I take the balloon and walk into the cooler up in Joshua's. When I walk into the cooler, it's very cold in there, so the particles are going to be moving less. As the particles move less, there's less collisions against the sides of the container, in this case the balloon or the piston. Well, if I consider the balloon and the collisions are less because the temperature's dropping, what happens to the volume? The volume decreases. Okay, so as temperature decreases, volume decreases according to the kinetic molecular theory. The last thing I'll consider down here is going to be volume and number of moles. Very simply put, if I take a balloon and I blow air into it, I'm increasing the number, I'm increasing N, I'm increasing the number of particles or the moles of particles. So as number of particles increases, volume increases. Okay, this is assuming pressure and temperature staying constant. Again, temperature and pressure are constant. Okay, next slide. Okay, the root mean square velocity. Basically, you guys can copy this down and take a look at that. Some things I want to involve you with. This is, of course, the velocity of particles, how fast they're moving. And what this says is that you have 3, which is a constant. You have R, which is a constant. You have temperature, which is something that's measured. Notice R is a little bit different in this case, guys. But the thing that I want to really point out to you is the molar mass of these particles here. The molar mass of the particles, especially the molar mass being in the denominator, says that the heaviest particles, which makes this number big, this number is going to be big, says that the heavier particles move slower. So you might want to write that down in your notes. Heavy equals slower velocity. Okay, or a lesser velocity. Okay, that's the big idea here. Okay, I don't know why we're doing that. Okay, so heavy, slower particles. If I get faster particles, they must be moving at a greater temperature or they must be smaller. Okay, so that's the root mean square velocity. And we're not going to do any calculations with this. You need to know this concept, the concepts behind the root mean square velocity. Okay, the last thing is effusion and diffusion and effusion. One slide too many. Okay. What we have here is diffusion is the random mixing of gases. Random mixing of gases. This basically says that I don't know why that keeps popping up. This basically says that as the particles are, as somebody in, let's say, the back of the room spray, dang it, I have no idea what's going on here, guys. I don't know why it keeps doing that. Anyway, okay. Okay. So with diffusion is the natural mixing of the particles. Effusion is gas moving through a small hole. Real simply put, that's all these things are. Now, I know you've heard of diffusion. It was something in the back of the room. Somebody sprays on some Bath and Body Works or something like that. Eventually, everybody in the room will smell this, especially people. The slowest people to smell this is going to be in the farthest corner of that person. Why? Because gas particles are constantly moving according to the kinetic molecular theory. Effusion, if you take a look at your book, I think it's page 2. Let me get there and I'll tell you what it is. I think it's page 209. Oh yes, page 206. There's a picture at the bottom of the page, like an orange box separated by a blue divider. If you take a look at that picture, it shows you what effusion is. Okay. Finally, the Graham's law of effusion basically says that the heavy particles effuse or move slowest. So this sounds a lot like the root mean square velocity, but basically it says that heavy particles move slower. Okay, so Graham's law of effusion says that if I have a heavy particle moving through a small hole versus a small particle moving through a small hole, the heavy particle will move slower than the small particle. Okay, that's it. If you have any questions, you guys can email me, which is st_kingkoff at smfcsd.org. Okay?